Welcome to lecture 35 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this lecture, we will mainly solve some numerical problems based on the topics covered in this week. In last lecture, we have discussed carrier tunneling mechanism in a semiconductor heterojunction, also in metal semiconductor and metal insulator semiconductor junctions. Except the last lecture, other 4 lectures in this week, we discussed optical modeling and carrier recombination models. So in this lecture, we will solve some problems based on the topics covered in this week. So we will have a problem, numerical problems on reflectivity of multi-layer structure, how to calculate the reflectivity and transmissivity of a multi-layer structure. Also we will discuss with the numerical problems on carrier lifetime and SRH recombination rate we will calculate for a particular problem. So this is a problem 16 according to the serial number of the tutorial problems. So this is basically problems on optical modeling or characteristic matrix. Problem is stated in this way. Suppose you have a multi-layer structure. Multi-layer structure, here we have considered 3 layers. Top layer of thickness D1, that is 0.5 micron, and the z-axis or z is equal to 0 starts from the interface of this layer with the air. Then this is another interface between first layer and second layer. The second layer is nothing but 200 micron thick. That means it is basically absorber layer in a solar cell structure, wide enough. And below this there is another layer of thickness 1.0 micron. NK values, that is real part and imaginary part of refractive indices for the layers, are also mentioned as N0 K0, that is air, N1 K1, N2 K2, N3 K3, N3 comma K3, in this way. And to use the formula whatever we have discussed in the optical modeling, the interface coordinates are very important. If the thickness of this layer is D1, this coordinate will be D1 directly. But if the thickness of the second layer is suppose D1 dash, then the coordinate of the interface between second and third layer will be Z is equal to D2, that will be D1 plus D dash is equal to D1 plus D1 dash. Suppose this is D1, this is D1 dash, this is D1 double dash. That's only thickness. So this coordinate will be D2. We are mentioning at a D2 for sake of simplification to use the formula. And D3, that is the coordinate of the last interface, that is the interface to the last layer, third layer to the outside media, that will be nothing but D1 plus D1 double single dash plus D1 double dash. Be careful about this. Now all these values are given. Assume normal incidence of light. Normal incidence of light means the theta incident theta is 0. Also the inside this first layer, that also theta you can take as a 0. So theta is equal to 0. Values of N1, K1 are given at a particular wavelength, say 600 nanometer. Because these values will change with the wavelength. AR media, this N is 1 and this is very less value, of course. N2, K2 also given, N2, K2, these values. N3, K3. These values are given. Calculate R, capital R, that is reflectivity, that is reflection coefficient, energy reflection coefficient and transmission coefficient or transmissivity of the whole structure. How can we proceed? We know the relationship between the 0 and D in this way. But D1, what is D1? D1 is here. So interface Z is equal to 0 and interface Z is equal to D1. So this relationship, so E0, H0 will be some matrix M1, ED1, HD1 at the interface D1. Again, ED1 and ED2, that is interface in the one interface this and at interface, they are related by this formula. D1 is equal to M2, say ED2. Actually, main thing is you have to consider a layer and it is surrounded by a top layer and a bottom layer. So you have to consider in this way. So whenever we are considering the first layer, it is surrounded one side by air, another side is surrounded by N2 layer. Or whenever we are talking about the N2 layer, it is surrounded by in top side N1 layer and bottom side N3 layer. So D1 and D2, they are related with this another matrix called M2. Now if you put this ED1 value from this expression to here, so it will become M2 into this and M1 already. So M1, M2, ED2, HD2. That means now E0, H0 is related to the E at D2 interface and H at D2 interface. So gradually it is increasing. So E0, H0 was related to D1, D2 electric fields. Now it is related to the D2 interface electric field and magnetic field. Similarly, you can increase. So there will be M1, M2, M3 and so on. So ultimately you can get the relationship between the electric field at top and electric field at the bottom. So this is say E0 and suppose this is ED, this is D1, D2, D3. So E0 and ED3, they are related by some product of matrices. Now what is M1? M1 is the matrix of the first relationship. As per the definition, this will be cos phi 1 j sin phi 1 by y1. 1 stands for the N1 layer. This is for N1 layer. This is N1 layer. Say this is N1, this is N2 layer, this is N3 layer. N3, N1, N2, these are the refractive index real parts. So that's why we are calling it N1 layer, N2 layer and N3 layer. J sin phi 1 by y1, J y1 sin phi 1 and cos phi 1. So we need to know the phi 1. Phi 1 also we know, that is twice pi by lambda n d cos theta. But here we have to put n1 d1 cos theta. And y1, that is optical admittance of the n1 layer, that will be root over of epsilon 0 by mu 0 n1 cos theta. Here also this is for TE polarized light. We have assumed that the incident light is TE polarized. That's why we use this formula. So if you put n1 and cos theta is cos 0 because in normal incidence. So by putting this value we can calculate m1. What will be m2? M2 is basically related between D1 interface electric field magnetic field to the D2 interface electric field magnetic field. And M2 will be then cos phi 2 J sin phi 2 by Y2 and similarly in this way. But what is phi 2? Phi 2 will be twice pi by lambda N2 then cos theta, and y2 will be epsilon 0 by mu 0 into cos theta. D2 minus d1 cos theta must be there because why it is there? The thickness of the second layer, it is the coordinate d2 and this is the coordinate d1. So thickness of the second layer which is produce the phase change only due to d2 minus d1. That's why we have used d2 minus d1 cos theta. So this d2 minus d1 term should be there. Sorry. N2 into d2 minus d1 cos theta. This is the product term. And y2 will be epsilon 0 by mu 0 n2 cos theta. There is no relationship with the thickness of the layer. So again this theta is 0 because it is normal incidence. So we can assume that it is propagating through the normal, along the normal of the surface. That means in all layers in angle of the beam, angle of the light can be considered as a 0. And for M3, how can we calculate M3? M3 will be related to the third layer. In that case, phi 3 will be twice pi by lambda d3 minus d2 minus d1. This should be maintained. And also similarly y3 can be calculated. And the final relationship between E0 H0 and ED3 HD3, this can be related by M1, M2, M3. So after extracting the values M1, M2 and M3 individually, we have to make the product of matrices to get a single matrix. So let us first calculate M1. So in last, here we should mention here Y3, that will be is equal to epsilon 0 mu 0 N3 cos theta. And cos theta is same, I have assumed, for a normal incidence in all layers. So in this way you can calculate the Y3. So after calculating M1, M2, M3, we have to take the product. Let us see how M1 is calculated. Because this calculation is required, I am showing one calculation of one particular matrix. It is a huge time taking and cumbersome job. Generally it is done by computers, but we should know how it is calculated. And during calculation some difficulties you may face. That's why I am showing how to calculate. So let us first calculate the phi 1. This twice pi by lambda n1 d1 cos 0. If you put the value 600 nanometer, n1 is 3.88 is given, cos and d1 is 0.5 micron, 0.5 into 10 to the power minus 6 or cos 0 1. So this becomes 20.31, but this is in radian. In radian, be careful in calculation. This is not in degree, it is radian. Y1 will be epsilon 0 by mu 0 n1 by cos theta. Cos term is 0, okay, but epsilon 0 you know 8.854 into 10 to the power minus 12 farad per meter, whereas mu 0 is twice pi 10 to the power minus 7 Henry per meter. This is very important formulas. 8 or values 8.854 into 10 to the power minus 12 farad per meter, and mu 0 will be 4 pi into 10 to the power minus 7 Henry per meter. and value of N1 is again 3.88 cos 0. After getting calculation, so you are getting 10.3208, that is the value of Y1. So M1 is cos 20.31, this is in radian, this is C small, J sin 20.31 by this, and after putting the values of cos 20.31 radian, sin 20.31 radian, this is the final value of the M1. There are two cross elements are associated with the J. There is a complex value. So similarly, you can calculate M2 value, M2, M3, and after getting all M1, M2 and M3, you have to take the product of three matrices, M1, M2, M3, and the final matrix will be, say, M in this sign I have shown, and which consists of ultimately the four elements. So matrix multiplication, perhaps you know, but you know the matrix multiplication here, suppose M1 value and M2 value I am writing. So this is suppose small m 1 1, small m 1 2, for M matrix, say a small m 2 1, small m 2 2. How can you take the product of these two matrix? Say M11 dash, M12 dash, M21 dash, M22 dash. You have to take the dot product. So this how to do M1 into M2, that I am showing. Is a matrix multiplication. So this row into column. So row and column wise. That means here 2 by 2 matrix M1, 2 by 2 matrix also M2. So the product will be also 2 by 2. Otherwise, number of rows of one matrix and number of columns of other matrix must be equal, and the final product will be the row versus column of another. So number of rows and columns in this way transferred. But it is 2 by 2, so no issue. So this will be nothing but M11, M11 dash into M11 dash plus M12, M21 dash. This will be the first element. And second element, this into this. That is M11, M12 dash plus M11, M12 dash plus M12 M22 dash, M11, M1 dash plus M11, M11, M2 dash, this row column, M11, M1 dash plus M11, M12 dash plus M12, M22 dash. And similarly, the third element will be M21, M11 dash plus M22, M21 dash. Yes, M21, M11 dash. And the third is, fourth one is M21, M12 dash plus M22 M22 dash. So in this way, you can get again 2 by 2 matrix. After multiplication of M1, M2, again you have to do multiplication with the M3. So finally you will get a 2 by 2 matrix with element M, capital M, N1. Capital M in that sense is a different symbol I have used with arrow, this underscore here. M11, M12, M21, M22. Using these final matrix elements, you can calculate the small r, that is amplitude, reflection coefficient and transmission coefficient by using the formula this y0 m11 plus y0 ys m12 etc. Be careful, this m11 is the element of final matrix, that's why the symbol like this, and y0 and ys, these are two optical admittances of top layer, that is AR, and ys is also AR here in this particular example, both are AR. So the total multi-layer structure, if we consider as a single layer, it is surrounded by top side AR and bottom side also AR. So y0 is equal to ys, and y0 ys will be epsilon 0 mu 0 in AR by cos theta, that is 10.3202 both cases. By putting this value into small r and small t expression, you can get r and t, but they are in complex form, that is a plus jb form both. Then you have to take modulus of these to get the capital R, that is energy coefficient. So that R value can be obtained from R modulus square. T also can be obtained. So the formula we have used in the class. So this calculation is a difficult thing. Generally we do programming so that computer can do the calculation, but how to calculate, and during calculation so many confusions where it is cleared that what values you have to use, how they will be coming complex. For that clarification I have shown only the calculation of a one matrix M1. Similarly you can proceed for other matrices and you can complete the calculation. So next problem, say determine the minority electron lifetime for density of defect states 10 to the power 14 per centimeter cube and 10 to the power 18 per centimeter cube. Given electron capture cross section 5 angstrom square, thermal velocity is 10 to the power 5 meter per second. Yeah, this is a straightforward. We have to use the formula. Which formula? You know, minority carrier lifetime is related to the capture cross section, thermal velocity and density of defect states. Basically, intention of this problem is to show the variation of carrier lifetime with change in defect density. So here minority electron lifetime, so it is a p-type material, understood. So tau n is equal to 1 by sigma n Vtn into Nt. We know this is capture cross section, sigma n for electron, Vtn is the thermal velocity for n electron, Nt is the density of trap states or defect states per volume, density of defect states per volume. Now let us calculate sigma n is equal to 5 angstrom square. That is equal to 5 angstrom means 10 to the power minus 8 centimeter. This will become 5 into 10 to the power minus 16 centimeter square. VTN is equal to 10 to the power 5 meter per second, that is equal to 10 to the power 7 centimeter per second meter. Yes. NT, first case NT is equal to, number one case NT is equal to 10 to the power 14 centimeter per centimeter cube. All are in CGS unit, no issue, you can calculate. So tau n in first case, it will be 1 by 5 into 10 to the power minus 16 into 10 to the power 7 into 10 to the power 14. Second, it will be obvious in second. You can check the dimension also. This is centimeter square, this is centimeter per second, so this is a centimeter cube per second. Second is in numerator will be going, so second, and then nt is per centimeter cube, so this centimeter cube and per centimeter cube will be cancelled out. So this is a second. 1 by 5 is nothing but 0.2 and 10 to the power 16 7, that is minus 9 plus 14, that is 10 to the power 5, 10 to the power minus 5 second. That means 2 minus 6 second, that is equal to 2 microsecond. And the second case, the same formula, if you use, tau n will be 1 by 5 into 10 to the power minus 16 into 10 to the power 7, all terms remain same, only change in nt, this is 10 to the power 18 in this case, and it will be coming at 0.2 into 10 to the power here 9, 10 to the power minus 9. Ten to the power 18, no, yes, 18. See, this is 0.2 nanosecond. So, how much difference occurs due to the change in defect density from 10 to the power 14 to 10 to the power 18? Generally, in case of thin film solar cell or amorphous structure, defect density varies from 10 to the power 13 per centimeter cube to 10 to the power 18 per centimeter cube. 10 to the power 18 per centimeter cube means your developed film is very poor quality. 10 to the power 13 is good, and if you use 10 to the power 14, if you see for 10 to the power 14 it is coming 2 microsecond lifetime, 2 microsecond lifetime, and if we would use 10 to the power 13 it would be further less, that is further less means 20 microsecond in that case. Anyway, that would be better than this. Carrier lifetime high means recombination rate will be less. Diffusion length will be also high. Carrier lifetime as large as possible is beneficial for reducing the recombination or for enhance the carrier generation. That is, a diffusion length can be enhanced. So carrier lifetime is very important parameter, and so in this problem it is shown that carrier lifetime drastically reduces with increasing defect density. This is another problem. Consider a p-type semiconductor is uniformly illuminated so that excess carrier generated per volume is 10 to the power 14 per centimeter cube. If the equilibrium carrier concentration of p-type material is 10 to the power 16 per centimeter cube, determine the rate of SRH recombination, given carrier lifetime of electron and hole are 25 microsecond and 50 microsecond respectively. An intrinsic carrier concentration of semiconductor material at 300 K is 10 to the 10 per centimeter cube. Okay, so our intention is to calculate the SRH recombination rate. We know, if you remember the formula, SRH recombination rate R is equal to the value Pn minus Ni square. Pn is after illumination concentration of hole and electron, the product of this. So Pn must be greater than Ni square, divided by tau Pn plus Nt, tau P plus tau N P plus Pt. But this is a actual formula. For approximate formula, we know there are two things. R almost equal to, in case of p-type semiconductor, it is minority carrier is electron. So delta n by tau n. If delta n less than P0, that is low level illumination, and R almost equal to delta n by tau n plus tau p if delta n not much less than P0, that is high level illumination. So delta, you know that delta P is equal to P0 plus delta P, N is equal to N0 plus delta N. Delta N is the photogenerated excess electron density, and delta P is the photogenerated hole density, that is excess hole density. How can you calculate this? That can be calculated from this. Excess carrier generated per volume is 10 to the power 14 per centimeter cube. So delta N will be 10 to the power 14, delta P also 10 to the power 14, but P0 is given 10 to the power 16. So here this is solution. So P0 is equal to 10 to the power 16 per centimeter cube. Delta N is equal to 10 to the power 14 per centimeter cube. That means delta N not much less than P0. So high level illumination formula we have to use. For that we need both tau n and tau p. That's why R will be delta n by tau n plus tau p, that will be equal to 10 to the power 14 divided by 1 is 50 and 25. So 75, sorry, write down 25 plus 50 into 10 to the power minus 6. So that will be 10 to the power microsecond, yeah, 10 to the power 20 by 75. Per centimeter cube per second. Rate of this recombination. So this will be the rate of recombination. Only catch of the problem is we have to check whether the low level illumination formula you use or you need to use high level illumination. We have to calculate first the delta n. Delta n already given, and in other case also, if the problem gives you the optical intensity of light, intensity, that means milliwatt per centimeter square, you have to calculate first the delta n and delta p, that is excess carrier density. Then you have to compare whether this minority excess carrier density is much less than majority carrier density at equilibrium or not. If it is that, then low level illumination can be assumed, and if they are comparable, high level illumination needs to be considered. In this case, 10 to the power 14 is delta n and 10 to the power 16 is the majority carrier at equilibrium. So they are not, delta n is not much less, you cannot neglect that. So in that, high level illumination formula can be used. So with this, we have, in this lecture, we have solved numerical problems, and we have shown how to calculate the characteristic matrix to find out the reflectivity and transmissivity of a multilayer structure. We have also shown by numerical problem how the carrier lifetime, minority carrier lifetime, drastically reduces with increasing defect density. These are the references. Thank you.